So, ladies and gentlemen, let's continue with the same topic, CFD algorithm. And in previous lecture, I was talking about the mass conservation, and this lecture I'm going to talk about the forces acting inside the control volume, and we'll see that how we'll do the balance, and then after we'll talk about the more things like that other multiphase related and K epsilon model, and then we'll go for the computation, how we'll do the computation, and how we'll insert that this equation and in a specific physical action, and let's see how we'll do this. So just I'm going to do it. Let's see. So let's see how we'll do that force balance in a control volume. So just I'm going to take one control volume here. We'll look at this. How I'm going to do is, so this is our control volume, and fluid is entering here and leaving here in a certain direction. In a certain direction means x direction, and leaving here in the x direction, and y direction and leaving in the y direction. And z also I'm not going to represent because this will be the more complex. So z I will write by myself. So already you know is equal to already you know about the force, Newton's law of second motion. Newton's second law. Force vector is equal to m dv by dt. So let's see how many forces will act here. So first, body force that is called gravity force will act, and the second one is surface force. Surface force means pressure force and viscous force. In viscous force will act normal and shear stresses. So if we look at this corresponding area and this plane, this is x plane. So I'm going to write this sigma xx, this is the stress, and if you multiply by delta y delta z, this corresponding area, suppose this is delta x, this is delta z, and this is delta y. So this will be your force, and this force will act in this way, and at a time pressure force will also act. So this will be the compressible in nature, so it will act like this. So here also it will act like this. So based on Taylor series expansion, we can write it sigma xx plus d upon dx into sigma xx into dx, and you will multiply by delta y delta z corresponding area, then you will get it the force. And this notation sigma xx, how I'm writing is, so this, suppose x is for direction of the force and this x for the plane, this x plane. So in that way we are writing, and this representation sigma xx include minus p plus stress. So this normal stress and this normal pressure will be normal. So if you look at this y direction, same we can write that sigma yy and delta x into delta z, this corresponding area, this plane, and again we will write that sigma yy plus d upon dy into sigma yy into dy delta x delta z. Okay, so this pressure force and plus this sigma xx and whatever the yy include pressure plus normal stress bar. So if you look at this tangential stress through this plane, if you consider a direction downward direction, so for this plane we'll take it as anti-clockwise, so you will take it upward direction. suppose this plane you will take upward, so this will take downward. So for this plane, if you will take tangential acceleration in this way, so here we will keep it like this way, that opposite to that. So what we'll do is, suppose your tangential stress is tau xx, not tau xx. Through this, what I told this we are taking direction of the force. So suppose this is the direction of the force, the first tau y, and the plane what, xy. So tau xy into delta y delta z will act here as a tangential stress. And then if you look at here, this leaving part, so tau xx, tau xy into plus d upon dy tau xy into delta y delta z. So if you, and that normal and shear stresses for z direction also we can write it sigma zz into delta x delta z, delta x delta y, and that leaving part we can write it sigma zz plus d upon dx d upon dz sigma zz into dz delta x into delta y. So if you look at this, what I was talking about, the tangential stress, if you look at this we have taken this direction, this downward direction, this upward direction. If you take as a this direction, so here will leaving part will again take in this direction, opposite to that whatever previous we have taken. So in that way you can write it that again stresses will come. So then this plane also you can write it, and then after what we'll do, that all forces, and that what equation, Newton's law, I've written it, force is equal to mdv by dt. So based on that, sigma fx and sigma fy, then sigma fz. So finally we'll get it one equation, and that will be the momentum balance and momentum equation. So next video will go for first I will write that equation that will help in computation of that, and then after, if you look at the K-epsilon model and other if you look at this software, ANSYS, COMSOL, and CMSCAL, XFlow, FlowVision, this related CFD related software, they already this software developed by this equation, and they are taking some specific physical action and dealing by this software. And suppose you are in ANSYS, something is not, suppose multiphase action they didn't consider here. So if you are going to do, if you want to deal this multiphase action, like in multiphase system is particle settling, you are doing that. You want to do CFD modeling and the optimization and whatever the time optimization, and if you are going for the validation, so analysis. So if you are going for this new things what I'm talking, so you have to write you need to write CFD codes related to this, and then so that is that mostly I'm talking about that only, but the things we'll talk that this whatever already existed. So mostly I'm talking new things I will do that related to the all heat. Suppose you are going to design a chemical reactor, either biological reactor, heat exchangers, and other things also you are going to optimize related to just related to suppose solar plates and other things, and based on FE also, stress and something else. So we can do that, and next video I will come with the heat transport, and before that I will write that equation also, but in this video I'm not writing that. So we'll look at that, slowly we'll go for that what I'm talking now. So okay, thank you very much. So I didn't able to write that body forces. So we'll take it body forces also. This suppose in x direction, y direction, and z direction. This is rho g z, rho gx, rho gy. This is our body forces, and this is per unit volume. So if you want in total control volume, so you have to multiply by the volume. So this is our body forces, and this will be also included. So after that, so that we have to also consider, and then we'll get it the total force. So then after we'll do that balance based on the Newton's law, and then we'll get it the equation. Okay, thank you.